Let's look at testing solutions in two unknowns. Here's our coordinate system, and just to set the stage so you'll understand what we're going to be doing, let me try to explain. In the past, what we've seen is that we can set up points, and this is just review. For example, 2, 5 means I go over to the right 2 and up 5. 1, 3, I go to the right 1 and up 3. 0, 1 means I don't go left or right, I just go straight up 1. Notice I indicated also these are our coordinate pairs. X is the first number, Y is the second number. Notice that I've set these up in a particular way. I've set these up so that each of these coordinate pairs actually solves that equation. For example, if I put a 2 for x, I get 2 plus 2 is 4, plus 1 is 5. Guess what? 5 is the y coordinate. And what we're going to investigate is that if those pairs solve that equation, in other words, if the equal sign still holds, what I will be able to do in every one of these cases is draw a straight line through those points that represents all the possible solutions to that equation. Notice there are two unknowns, x and y. We'll get there. I just wanted to give you a hint of what was coming so that you will understand how we're going to flow. Let's suppose we have a Cartesian pair, a pair of coordinates, 2, 3. X is 2 and y is 3. Then we have an equation in two unknowns. And the thing to look at here, up to this point we've been dealing with equations in one unknown where we can manipulate things, move numbers around and so forth, and get a solution. The problem here is that if I try to solve for x, say by subtracting y from both sides of the equation, since I don't know what y is, I can't arrive at a numerical solution for x. And the same can be said for y. You can't solve these without two pieces of information, the value of x and the value of y, or you can't at least check these without two pieces of information. And you're certainly going to have to know what y is to get a solution for x, or you're going to have to know what x is to get a solution for y. Right now, we just want to test to see if the pair 2, 3 is a solution. If we put 2 in for x and 3 in for y, what will happen? I'm going to do that. I'm going to substitute 2 for x and 3 for y and test to see whether the pair 2, 3 is one of a possible multitude of solutions for x plus y equals 5. I substitute that in, 2 plus 3, 2 for x, 3 for y, and sure enough, 5 equals 5. So I would say that yes, the coordinate pair 2, 3 is a solution to that equation. Let's test another pair. Let's put 0 in for x and 8 in for y and see what happens. When I make this substitution, I get 0 plus 8 equals 5, and 8 does not equal 5. Whoa, hold it. We say no, the pair 0, 8 is not a solution to x plus y equals 5. Again, we can test these, and the idea here, when we test variables to see if it's a solution, we replace the variables by the values in the coordinate pair and ask ourselves, is the equal sign still valid? And you see in this case, of course, just by observation, 8 is not equal to 5, and this is not a solution. Let's try some others. What about 6, 5 in the equation 2/3 x plus 1/5 y is equal to 5? Is this a solution? I plug these in, and then I try to evaluate 2/3 of 6. 6 divided by 3 is 2. 2 times 2 is 4. 5 divided by 5 is 1. I have 4 plus 1 equals 5. 4 plus 1 is 5. Guess what? The pair 6, 5 is a solution to the equation 2/3 x plus 1/5 y is equal to 5. Yes, indeed, that is a solution. Now, let's go a step further and see if we can reverse the process, take an equation and two unknowns, and find a series of solutions for those equations. What we did up to this point was just test. We were given two values, an x value and a y value, and we plugged them into the equation. Now it's asking for a little bit of original thought. We're going to be given an equation and asked to generate values. Let's see how we do it. First, we can set up a table, and then, for example, here I have the equation y is equal to 2x plus 1. What I want to do is go through a series of values for y. Given those, I want to solve for, I want to go through a series of values for x, and given those, I want to solve for y. Let's try this. I'm going to solve for the case where x equals 0. And the reason I picked 0 as opposed to 357 is I try to think ahead when I do this and look for things that will give me simple solutions. If x is equal to 0, then 2 times 0 is 0 plus 1 is the value for y, and I've generated y is equal to 1. So that pair is, in other words, now I've generated a coordinate pair, x equals 0, y equals 1, that is a solution to the equation by picking one value and then solving for the other. Let's try another one. Suppose I set x equal to 1. What's y? 2 times 1 is 2, plus 1 is 3. Let's try another value. Suppose I pick x equals 2. What's y? 2 plus 2 is 4, plus 1 is 5. Incidentally, this is an interesting equation because look what I've generated, 1, 3, 5. It looks like as I plug x's in, 0, 1, 2, 3, 4, 5, I've generated odd numbers. Kind of interesting. What we've done here is seen that the value of y depends upon the value of x. And you could also say vice versa, but the way this equation is set up, I know that it's easier to put in x and look for y. So here's what we do. We choose a value for one of the variables and then solve the resulting equation for the other variable. I can also make this link. X equals 0 when y is equal to 1, x equals 1, y equals 3, and so forth. I can think of those solutions. There are three solutions, and again, I could, for example, pick x equals 273 and solve for y. There are as many solutions as you want to think of in terms of pairs for these kinds of equations. I can think of these as ordered pairs, 0, 1 in this case, 1, 3, and 2, 5. Then if I have these ordered pairs, let me plot them. Let's see what's going to happen here. If I plot these three pairs of numbers, these three ordered pairs, 0, 1, I don't go at all left or right, I go up 1. 1, 3. I go to the right 1 and up 3, and then 2, 5. I go to the right 2 and up 5. Notice that all three of those ordered pairs are solutions to the equation 2x plus 1 is equal to y. Notice that those things fall in a straight line, and in fact that straight line represents every possible pair of solutions for that equation. For example, if we look over x, where x goes to 3, and then follow up until we see where that line crosses at y, we see y equals 7. Let's try that. Suppose x equals 3 when y equals 7. Is that the case? 2 times 3 is 1, or 2 times 3 is 6, plus 1 is 7. So in fact, what we've done by choosing 3 points, and drawing a line through it is that line now represents every possible pair of solutions for the equation 2x plus 1 is equal to y. Notice that when you deal with geometry, how many points does it take to determine a straight line? 2. In other words, if I have a point here and a point here, I can draw a straight line through those points. Yet I did something on the slide. Instead of being lazy and only plotting 2 points to determine what that line was that represents all of the values for that equation, what I did was plotted 3 points. And the reason is the third one is a safety. If, for example, I have 2 points and then one, and so the line I would have to hook them up with is crooked, that would tell me that at least one of those 3 points was not calculated correctly. If the minimum number of points you need to do this is 2, I would recommend always using at least 3 just to make sure that what you're going to do comes out on a straight line. Let's look at a few other examples. We first, as I said, find 3 ordered pairs. Some will tell you 2, but 3 is important. You plot the solutions of those things as points. You connect them with a straight line. And one of the things you can do is go for the easy points. For example, if you let x or y equal 0, one of those terms is going to go away, which will make your solution immediately easy. For example, if I put a 0 in for x there, I'm left with a relatively simple equation, 1/5 of y is equal to 5. Multiplying both sides by 5, I get y equals 25. So I've let x equal 0 in this case. Now let me let y equal 0. If I put a y equal to 0 here, then I have the equation 2/5 x is equal to 5. And when I solve this, multiplying both sides by the reciprocal of 2/5, 5 halves, I wind up with x is equal to 25 halves, or 12 and a half. I've made at least a couple of calculations much easier for myself by letting x be 0, then letting y be 0, and then I don't have to subtract a number from either side of the equation to solve it. I can do it a lot faster. Keep that in mind as you're solving these things. Always use zeros where you can. Let's try another one. X plus y is equal to 4, and do what I said. The first thing I would like to do, just to make this equation maybe a little bit more straightforward, is subtract x from both sides. So whenever I put in a value for x, I will have the y value immediately. You don't have to do it this way. You could just put a value in for x and then solve afterward for each one of these cases. Sometimes it's better to do it one way, sometimes better to do it another way. You take your pick. In this case, I thought it would be easier if I initially solved for y in terms of x. Now, let me put x equal to 0. What do I get? Y equals 4. How about x equals 1? This is pretty rough here. Y is equal to 3. And if I use x equals 2, I get y is equal to 2 as well. And we can then provide the ordered pairs 0, 4, 1, 3, and 2, 2. Now let's go plot these. 0, 4 is there. Because x is 0, we don't go to the left or right, we go up 4. 1, 3 is there. We go over 1 and up 3. 2, 2 is here. Notice we can tell right away these are going to form a straight line, and we're finished. And we can see again, if we look at this, we can see that in this case, everywhere along here is a solution to x plus y equals 4. For example, let's look right on the x-axis where y is equal to 0. Where does that line cross the x-axis? It crosses it at 4. So when y is equal to 0, x is equal to 4, and the relationship x plus y equals 4 holds. Here's one that's a little bit more interesting, and in this case I am not going to try to solve it ahead of time for y in terms of x, although I could. What I would like to do is just leave it this way and then work the solutions later. Let's plug in x equals 0 again. Notice how straightforward that makes things. When x equals 0, I have minus y equal 9, which says that if I multiply both sides by minus 1, I get that y is equal to minus 9. Let me choose another value. How about x equals 0? If x equals 0, then the equation becomes 1/3 x equals 9, multiplying both sides by the reciprocal of 1/3 or multiplying both sides by 3, I find that x equals 27. And that's another pair. 27, 0 is a solution for that equation. Let's try one more value. Let's try x equals 3. Notice that I pick values that make it easy for me to get solutions. Because if I pick x equals to 3, what's 1/3 times 3? It's equal to 1. Then I have 1 minus y is equal to 9. If I subtract 1 from both sides of the equation, I get minus y is equal to 8. Multiplying both sides of that equation by minus 1, or taking the inverse of both sides, as you will, we get y is equal to minus 8 when x is equal to 3. Now we have 3 ordered pairs, 0 minus y, 27, 0, and 3 minus 8. Let's go ahead and try to graph these. 0 minus 9. The 0 means don't go to the left or right, go down 9. 27, 0, and that's the opposite. In this case, I don't go up or down, I just go over 27 units. And finally, I have 3 minus 8, meaning I go over 3 and down minus 8. I'd like to call your attention to something else here. When you look at the graph, you see that I had to change the scale. That scale up and down and sideways doesn't go 1, 2, 3, 4, 5 anymore. Because of the points I picked, I see that in the x direction it has to go all the way to 27. So I rescaled it. Instead of going 1, 2, 3, 4, 5 for each of the little boxes, what I did is there are 5 boxes, so each of the small boxes is worth 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Sometimes when you're graphing equations, figuring out how to put your scale on the coordinates is a very important thing. The bigger you can make your graph, the more accurate, the better idea people will have of what you're doing. It's important to make sure that you have scaled things as far as possible. Try when you set your scale up to fill the whole piece of graph paper. Anyway, we've determined 3 points here. Now I can connect those 3 points with a straight line, and again, that straight line indicates all possible solutions for the equation 1/3 x minus y is equal to 9. Here's one that looks really weird. What about the equation x equals 5? What about the values of y? The point is, since y is not mentioned here, the only thing we need to do, according to this equation, is keep x equal to 5. Y could be anything we want it to be. For example, y could be 0. Doesn't matter, there's no restriction on y. Y could be 3. Y could be minus 7. It doesn't make any difference. What's this equation going to look like? There is 5, 0. There is x equal to 5, y equal to 3. and here is x equal to 5, y equal to minus 7. What sort of a line will that be? When you have the equation x equals something, what happens, since y can be anything, the equation x equals 5 generates a vertical line. And if x equal minus 4, it would still generate a vertical line, except that line would go through x equals minus 4. Let's try this one. How about y equals minus 3? You notice I have minus 3 for all values of y because the equation forces y to be minus 3. If y were 2, that equation would not be, that wouldn't be an equation. It would be basically, I guess it would be, well, never mind, it wouldn't be an equation. But now what I can do is choose any value I want for x. Doesn't matter what values I pick because x isn't constrained. The only constraint left to me by that equation is that y has to be negative 3. If I plot this, there is x equal to 3, y equal to minus 3. Here is x equal to 0, y equal minus 3. And here is x equals minus 4, y equals minus 3. And the only, I'm constrained that y must be minus 3, but x could be anything. When I do this, I get a horizontal line. When y is equal to minus 3, x can be anything, and that generates a horizontal line. So whenever you have only y equal to a number, you're going to get a horizontal line. When you have only x equal to a number, you're going to generate a vertical line. How about, here's an interesting one, well, I don't know, interesting, but how about x equals y? That's pretty hard to solve. If x is 0, y is 0. If x is 5, y is 5. And if x is negative 2, y is negative 2. Let's see what that's going to look like. We'll have the ordered pairs 0, 0, 5, 5, and minus 2, minus 2. Let's plot that. There's 0, 0, there's 5, 5, and here's minus 2, minus 2. And this gives us a line which is exactly 45 degrees. It cuts quadrant 1 and 3 right in half. We've talked about x equals 0 and y equals 0 being particularly easy solutions to get. In fact, they even have special names. Let's try another problem. 3x plus y is equal to 6. Let's put x equals 0, then y is 6. If y is 0, then I have 3x is equal to 6. Dividing both sides by 3, I can see that x is equal to 2. Let's try one more solution. If x is equal to 1, then I have 3 plus y is equal to 6. Subtracting 3 from both sides gives me y equals 3. Let's graph this. 0, 6, 2, 0, and 1, 3. There is 0, 6. X doesn't go anywhere. Y goes up 6. 2, 0. X is equal to 2, y is 0. And just to make sure we have a straight line, I have one more point in there. Now there are 2 points that I want to call your attention to where the equation of where the line of the graph crosses the axes. Where it crosses the y-axis is at the value x equals 0. That has a special name. It's called the y-intercept. The equation intercepts the y-axis at x equals 0. The equation intercepts the x-axis at y equals 0. So we can talk about those 2 points. They're special. They're called the y-intercept and the x-intercept. And again, just to reiterate, the x-intercept is the point where the line intercepts the x-axis at y equals 0, and the y-intercept is the point where the line intercepts the y-axis at x equals 0. Let's look at some of the applications for graphing equations. And one of these, you don't always have to use xy. You could use some other things. For example, suppose I want a graph to convert Celsius or centigrade to Fahrenheit. I can put numbers in here. Freezing Celsius is 0. And if I solve that, I find that the Fahrenheit equivalent is 32. Boiling Celsius is 100. And if I do the math there, I find that boiling Fahrenheit is 212. And I can pick some other value. How about 50 Celsius? And if I want to work that out, that gives me Fahrenheit 122. Then again, you see I changed the scale, but I can plot those points. And then I can get a line which represents every possible solution of the equation f is equal to 9/5 c plus 32. What this means is that I can look at any point along this line and know that's going to be a conversion between Celsius and Fahrenheit. For example, at the point where f is equal to 0, I can see right away, if I squint at it a little bit, that f equals 0 is equivalent, because it's on that line, to c is equal to roughly minus 18 degrees Celsius. If I want to test this out to see how close I am by estimating from that graph, I can say that f equals 0, then solve that equation, and I find out that it's actually, solving it algebraically, minus 17.7, and typically when you're dealing with temperature, 18 is close enough.